Right, this is a continuation of motion in a straight line. The first video we looked at distance and displacement and scalars and vectors in general. Now we're going to continue with the main measurements of this chapter. There's 5 of them. There's distance and displacement, which we looked at some, and then there's speed, velocity, and acceleration, right? If we handle those, then we really have accomplished everything for this chapter. Now there's a lot to it. We're going to look at this graphically. We're going to certainly look at this through calculations and calculating these types of measurements, and we have to understand what each one means. And being able to just give back the definition doesn't really prove that you know what these measurements mean. So let's start looking at these, or let's continue looking at these. All right, so the first 2 measurements are speed and velocity. Kind of like the last one where we had a distance, we had a scalar and a vector. Same thing holds true here. We have a scalar and a vector where speed is a scalar. The symbol that we're going to use is V, and the units are meters per second. Now, just to say that, I think I say it in another video, but what's the measurements we're going to be using in class? In class, we're going to be using kilograms, meters, and seconds. And later on, we're going to be using coulombs, but that's way down the road. So all of our answers are going to be kilograms, meters, and seconds, just to kind of reiterate that, something that I will have said before this video. So could it be in miles per hour? Sure, it could, if that was appropriate for what we're talking about. But for everything we do, we're going to use these units, kilograms, meters, and seconds. So speed's going to be measured in meters per second. That's going to help us. So if we get an answer, we're not worried about, if one person gets something and they did it in kilometers per minute and another person did it in miles per hour and another person did it meters per second, we can't compare them. Now, we're going to do them all in the same units all the time. So speed's a scalar, no direction associated with it. It is the rate a distance is covered, right? And it has to deal with distance because there's no direction, right? So if you're traveling 20 meters per second, you cover 20 meters in a second. It doesn't matter if you went in a straight line, doesn't matter if you did a circle, doesn't matter if you did this, right? It makes no difference. You covered that much distance in that amount of time. Vector is something different. It is speed in a specific direction. How fast did you go this way? Or how fast did you go this way? Something like that. Now, again, with that said, we tend to see that speed is just how fast you're going. It's the rate that you're covering a distance. Velocity, just like I'm pointing out, has a direction associated with it. And an object can have many velocities where it tends to have one speed. So let's say I have a table. Let's say I have a marble. And I roll this marble off the table. Well, at the top here, it has a certain speed, right? And it has a certain direction this way. And that's great. Its speed and its velocity are essentially the same in magnitude and units, and I know the directions to the right. But let's say the marble's here now. Well, now it's doing a couple things, right? Well, now it has a speed, and that's fine. And it has a velocity, it has a direction. It's going this way. But along with that, I can look at other things. I can look at how fast is it falling. So I can look at its vertical velocity. I can look at its horizontal velocity. How fast is it moving away from this table or away from this cliff, right? So there's a lot of different things that I could look at here, and I could look at 3 different velocities, and these different velocities tell me 3 different things. This tells me how fast it's going and in what direction. This tells me how fast it's moving towards me if I'm standing over here. This tells me how fast it's going down, or it's going to help me determine how long does it take to hit the ground, let's say, right? So they're going to be useful in different ways. So an object can have multiple velocities, but it only has one speed. So let's say I had this velocity graph. And again, we're going to do the same type of thing. We're going to look at a velocity graph, see if we understand what's going on with it. And then we are going to match that up with the displacer graph and see if we understand that. So first of all, I see that velocity is negative, which means we're moving backwards, right? It has a negative velocity. Velocity is a vector. It's okay to have a negative velocity. It means we're not moving forward, we're moving backwards. So again, if we assume this is a car and a car like starts this way, the car is going in the negative direction. Not only is it going in the negative direction, but the velocity is getting bigger, right? It starts out with a velocity of 0 and it gets bigger and bigger and bigger and bigger and bigger. So now we could say it's moving that way and it's speeding up. Whoa. Hold on here. going this way, and it's speeding up because the velocity is getting bigger. Now, one of the big things is people confuse these measurements, right? The speed graph is going to tell us different things than the displacement graph, right? In some cases, we can get some of the same information, but it's going to look different, right? And the velocity graph is going to tell us some things that displacement couldn't tell us, and displacement's going to tell us some things that velocity couldn't tell us. But the general information that it gives us, right, a lot of that crosses over, so we have to understand what graph we're looking at. So for this first part, we are moving in the negative direction because it's a negative velocity. The velocity is getting bigger, so we're getting faster and faster and faster. Now we have this horizontal line from there to there, right? What's happening there? Well, I still have a velocity, so I'm still moving. It's still a negative velocity, so I'm still moving in the negative direction. But it's a constant velocity, so I'm moving at a constant rate. Constant rate, or now that we define it, we could say, you know what, it's constant speed. And this was speeding up, getting faster. Now I go from here to here, still a negative velocity. So I'm still moving in the negative direction, but my velocity is approaching 0. So from there to there, I'm still moving in the negative direction, but I am slowing because my velocity is getting closer and closer to 0. I'm not moving in the positive velocity, right? It's a negative velocity, I'm moving in the negative direction. Now from here to here, now my velocity has become positive. So what's happened? I've turned around, now I'm starting to move that way, and I am speeding up. And that's from here to here. Again, I have a flat line, so I have a positive velocity, and it's constant. So now I'm moving this way, and again, it's constant speed, right? So both of these green ones are constant speeds. And then I'm still moving in the positive direction. It's a positive velocity, but it's getting less and less. So for this part, I am slowing. And then right at this point, what did I do? Well, here I stopped, just like I did here. These two places, the velocity is 0. I must have stopped. So again, it's telling us a lot. Which way am I going? Am I speeding up? Am I slowing down? Am I maintaining a constant rate? Am I not moving at all, right? All of these things. So let's look at my displacement graph. What would that look like? Well, for this first part, let's assume I start at 0. And that's one thing the velocity can't tell me. It can't tell me where I am to start this problem. It can tell me how things are going to change. So I have a negative velocity, and it's getting bigger and bigger and bigger. Means I'm moving in the negative direction and I'm speeding up. So what would this look like? Well, my displacement has to be getting more and more negative, and it's got to be getting steeper and steeper and steeper. I'm expecting this to be curved because I'm getting faster and faster and faster. Now this next part, I'm still moving away from the starting point. So I have a negative velocity, so I'm still moving away from the starting point. I'm still moving in the negative direction, but it's a constant rate. So what's happening here? Well, that's something, if I could draw a straight line, something like that. Now I'm still moving in negative, but I'm slowing down. So it's still going negative, but it's going to flatten out right there. It's going to flatten out. And we saw in the other one, when it flattened out, it's where we stopped. Well, this and this line up with each other, and this is where I stop. Now I am speeding up. So actually, you know what? My lines don't match up. So I'm going to say right here. Is that a highlighter? What is that? Undo. There we go. So this I didn't have a point for, so I'm going to say this is here. So I am moving away, and I come to a stop, so it flattens out right there. Now I start moving the other way. Well, I'm moving in the positive direction, and I'm speeding up, so that's going to be curved. I'm moving in the positive direction at a constant rate, so it's a straight line. And then I have a positive direction, and I'm slowing down, so it's going to do something like that. And then I stop. Now I'm done. And now if I kept going, this would be a straight line. So it's going to look something like that, where this is a curve, this is straight, this is a curve, this is a curve, this is straight, and again we have a curve. Right? So straight, curve, curve, So that's what my displacement graph would look like. If I wanted to do one more, let's clear all of this. If I wanted to change this and change it to speed, well, speed can't be negative because it doesn't have a direction, so what would it be? It would be just like that, and this is where I stop, so it's got to go down to a stop, and then it goes up, and then it goes over, and then it goes up. So we could argue that all of this is essentially flipped up because speed is just a positive number. All right, now for our final measurement of this chapter. I would argue that acceleration is the most complicated measurement to understand, maybe for the whole year, right? There's definitely people that struggle every time we come back to acceleration. So what is acceleration? Well, first of all, acceleration is a vector. There isn't a scalar form of this. It is a vector. It's measured in meters per second squared, and we're going to look at these units more in some of the mathematical examples in the next video. But what is it? It is the rate of change of velocity. So it's a couple things, right? It's the rate of change of velocity. So it's how much did the velocity change and how fast did that change occur? And it gets very confusing because when we look at something, we can kind of see how fast it's going. So we could see its speed, its velocity, right? We may not be able to, have radar eyes and get an exact value, but we could see if it's fast or slow. We could see distance and displacement. We could kind of visualize these things. Acceleration, though, very hard to do. So lots of times we confuse acceleration with velocity, and they're very different things. So acceleration is how velocity changes. Another thing that makes acceleration confusing for people is, by definition, it's a change in something else. When we accelerate, velocity changes. And when velocity changes, displacement changes, right? Everything changes when you're accelerating. When the acceleration's zero, well, nothing's changing. So you could be traveling down the highway at 60 miles per hour and my acceleration's zero. So what does that mean? That means nothing's changing about my velocity. I'm simply staying at 60 miles per hour, still going straight down the highway. So what are some changes that could occur? Well, the most common answer I get is I could speed up. Step on the gas, drive down a hill, something like that causes me to speed up. That is a form of acceleration. The other thing that I could do is I could slow down. I could step on the brake, I can go up a hill, I could take my foot off the gas. All of these things will cause me to slow down. So both of these are forms of acceleration. We're not going to get into deceleration because deceleration kind of brings in some false understandings of things, right? And again, we'll hopefully see some of that in our examples. The other thing I could do is, because it's a change in velocity, velocity has direction. How else could I change my velocity besides speed up and slow down? I can turn. So acceleration is a change in velocity, which implies if you're accelerating, you're either speeding up, slowing down, or turning. And again, just to kind of go back to the very beginning, we're dealing with motion in a straight line. So we're going to stay away from this, at least for now, right? We're going to deal with speeding up and slowing down, and we're going to leave turns for later. But there's certainly a possibility. Now, of these measurements, distance, displacement, speed, velocity, acceleration is the one that you notice is going on. If you imagine that you're in the car, you're sitting in the passenger seat of a car and someone else is driving, right? You can't feel distance or displacement. You can't feel, say, oh, that felt like 5 miles, right? You can't feel that, right? And you can't feel how fast you're going. You can't say, oh, that feels like 50 miles per hour, right? These things you can't feel. If you did feel your speed or your velocity, right, then flying in a plane would be horrible because you're going so much faster than you are in a car, but you don't notice that difference, right? You notice you're moving maybe, but even then, right, even then it's a little different. What do you notice, though? What do you feel? Well, you feel acceleration. You feel yourself speeding up, right? You have your eyes closed and the person driving the car speeds up, you feel that. You feel yourself slowing down. You feel yourself turning, right? So you feel all of these things. And that's important to understand, because what we're saying is acceleration is caused by a push or pull. Now, It's important to understand that because the direction of acceleration has everything to do with how it's getting pushed or how it's getting pulled. So it's a good thing to understand as we try and establish a direction of acceleration. And it's also a good thing to point out because we're going a little backwards through learning these things, right? We're starting with distance and displacement. Why? Because we all understand what distance and displacement is. Even if you didn't know the definitions of them, you understand lengths because you've measured things before. So it's easy to conceptualize those two things. It's easy to conceptualize speed and velocity. So we're starting with measurements that are easy to understand. We're not really starting with the cause of things. We're really looking at the effect, right? How do we determine something's displacement? Well, it has to do with its velocity and its acceleration, right? It's caused by how an object moves. If we want to know something's velocity, well, that's caused by its acceleration. It's caused by how the velocity is changing. So if I want to know how fast that was going 10 seconds later, I got to look at acceleration. Acceleration causes the change, right, by definition. So in cause and effect, we're kind of working backwards. So to fully understand acceleration, that's going to take a decent amount because we're going to have to look at these pushes and pulls in detail later. But just understanding that our push or pull is what causes something to accelerate, well, then that's useful in understanding directions for acceleration. All right, so we're going to stay away from a lot of fancy accelerations. We're just going to stick to constant accelerations, and that's works out very well for us, right? There's really no reason for something to have a constant acceleration. Um, but we're going to assume that just because it makes this section a little easier and this section's hard enough, right? So these situations we're talking about, there's a constant acceleration. So for this period of time, there's a constant positive acceleration. And then there's a constant positive acceleration that's just smaller. Then there's an acceleration of 0. And then there's an acceleration that's negative. Just by looking at that, I say, okay, something's pushing this object forward. Something's pushing this object forward, but it's not pushing as hard as it was before. It's less acceleration, right? And if acceleration is caused by the push or pull, then something's pulling it in the positive direction a lot. Something's still pulling in the positive direction, just not as much. Nothing's pushing, pulling on it at all. And that might not be the perfect statement, but again, as we get into pushes and pulls, we'll see. But the net push or pull is 0. And then something's pushing or pulling it in the negative direction. So we have these different accelerations, right? 4 of them, if you will. There, and then here we have those. So if I was looking at velocity with respect to time, well, what's happening? And again, this graph doesn't tell me what my initial velocity is. I could be going in the negative direction already. I could be going in the positive. I'm going to assume it's 0 because the shape is just going to shift up and down. If it experiences a constant positive acceleration, what's the velocity doing? Well, the velocity is increasing, right? And then I still have a constant positive acceleration. It's a different one, right? But I still have one. So is it increasing? Sure, it's increasing. But it's not increasing at this rate anymore because it's less of an acceleration. So it's increasing at this rate now. And then I have an acceleration of 0. Well, if acceleration is the rate of change of velocity and the acceleration is 0, the velocity is not changing. It doesn't mean it's not moving. It means it's not changing. If you pretend that's a horizontal line, it would look something like that. Now I have a negative acceleration, which means the velocity is changing in a negative way, which means the velocity that was positive is changing by a negative amount. So that means I must be slowing down. So there would be my velocity graph. It's changing in a positive way, and it's a big acceleration, it's a big change. It's still changing in a positive way, but it's less acceleration, so less change. It's not changing at all. It's a horizontal line. Now it's changing in a negative way, a constant negative way, so it's going down. Just to finish this up, if I put displacement on this same graph, well, it's moving in the positive direction, so I'd expect my displacement to be going up in the positive direction, and it's getting faster, so it would be something like this for that amount of time. Now it's still going up, we're still speeding up, so it's still getting faster, but it's getting faster at a less drastic rate. So it's still going up, and it's still speeding up, but this curve is not as steep as this curve. And then I have a constant velocity. Doesn't mean I stop moving, just means I'm moving in a constant rate. So it's just going to be a straight line where this was a curve and this was a curve. This is now straight. I'm still moving in the positive direction. So I'm still moving away, but it's getting flatter. So it's going to be curved this way. Again, that's going to be curved. So if I knew my acceleration, I could see how that changes velocity. If I know my velocity, I know how that changes my displacement. The only thing that I'm assuming on these graphs is where I start from. The shapes, this black lines that I drew for velocity and the red lines I drew for displacement are going to look the same. It's just where do they start on these axes is the only thing that could change. I could say, hey, I'm not starting at a displacement of 0. I'm already 10 meters away from my starting point when all this occurs, right? So I could shift these up and down on my graph. I don't really change my picture too much. All right, so that is a general definition of the 5 measurements we need to know. We're going to look at these mathematically. Again, our goals are to see what the positives and negatives mean, how they affect direction, how one measurement has an effect on the other. Okay, let's continue from there in the next video.